start the third day of the workshop. So we are very happy to have Professor Hosono again. He will continue his talk on the families of Calabi-Yau manifolds and the mirror symmetry.
Thank you very much. Last time, at the first talk, I focused on the toric hyposurfaces in toric varieties, and this time I'm going to show the very special Calabi-Yau manifold, which is not inside toric variety. Inside toric variety, the construction is not in. It is not in terms of toric geometry. But any guess, the 90 minutes, so it's enough. So I'm going to use slides in total 20 or 21 slides, which I used for 60 minutes. So, maybe I'll somehow I'll explain details. I can explain. Anyways, as a beginning, so let me recapitulate what I said as a definition of mirror symmetry. The definition of Calabi-Yau, so again, my focus is Calabi-Yau 3-4, and then the definitions are just a lot of yesterday, the downtown material and the homology condition like this. And then given us this kind of Calabi-Yau 3-4, we have the two structures, as I said. One is the A structure related to the scalar class. So this time, so last time I wrote simply the scalar form. So this time, scalar form together with its dual form, so called net form. I wrote simply in here the scalar form. And then on the other hand, this structure is defined by in terms of family of Calabi-Yau manifolds. So this is not the case. That in case of toric hyposurfaces, there is natural way to construct family. By definition, from the very beginning, we know how to construct family from there. So in this, given a family, and then we have the local system associated with this, and then we can work out so-called field integrals. And then you got the focus on the special model from here. Originally, this spatial projective or very local, but we got this kind of local system. Then you know that this local system is called Gaussian system, is regular singularity type, and then the making a local solution, then you can think about the analytic continuation to the much larger domain or the defining domain. And then so that's one way to see how to come to the compactification of the model space. And it's a nice compactification somehow we want to know, we want to find out which is compatible with this local system. And then the assumption is that the finding such a nice compactification, and then they focus on it, try to find out some special boundary point given as the intersection point of normal crossing boundary devices. And then from there, I described the B structure. Now a little bit details. I would like to explain. This time in duality. So one side, as I said, the scalar form and the net form as I dual form. And then on the other side, so for the B structure, just I assume from here, suppose we have nice compactification in bar and find out boundary divisor and intersecting at the boundary point. But usually, even in this situation, this is singular. So what we do is this coordinate ring of this coordinate ring, which is described whose origin is O, is still singular. So what we do is consider the dual form, and then And then, so because of singularity, just subdivide this diagram, and then that corresponds to the growing up at this point in something like this. And then, again, if this is singular, then we will consider the boundary point, again, the normal divisors. This time using the exceptional divisors. So in any case, so this time I'm paying a little bit detailed story. Even if you find boundary point, usually typically such boundary point is singular, so we need to blow up something like this. And on the other hand, and then maybe I should be here. And then so is R1 and R2 is the ray generator of this dual cone, and then associated to so these rays correspond to divisors, and then so I made this rays of cone. It's R1 and R2, then each correspond to the boundary divisors, and this picture is not so strict. So R1 is let's say notation is something. This size should be D1 for consistency. This divisor, this device should be the something inconsistency here. But in any case, the regenerators and the boundary divisor, there is a correspondence, not a correspondence like this. And then focus on the monodromy around the boundary divisors. I denote T1. T1 is monodromy around the boundary divisors, which described by this ray generator, correspond to ray generator. And the same thing for these boundary divisors, which we can characterize by the ray and therefore sigma. This sigma prime this is a monodromy generator. This is a little bit detailed things, but in any case, so if the assumption is these divisors, so if we start from special boundary point, then this monodromy transform are unipotent. So if we find out such a boundary point, then we can consider the general linear combination. So lambda I is general parameter, positive parameter, supposed to be positive parameters, and they take linear combinations, and then the associations of this log Ti is unipotent, which is commuting. So this general linear combination is also commuting, and gives us unipotent actions on the H3, as I said yesterday. And then, so assumption is that we have unipotent action on the H3, and the assumption is that this kind of iteration from Jordan form of unipotent matrix. That's the assumption for the special boundary part. And correspondingly, the A side is what we do. So what we can figure out is that so last time I assumed Kerakon is simplicial, but in general Kerakon is very complicated structure that the main issue for high dimensional geometry. And so that corresponds to this growing up process. So to resolve singularities after resolution, so this cone, your cone is regular, to resolve seniority here. So that's corresponds to that. So given a Kerakon, it's usually typically very complicated shape. But in such a case, subdivide Kerakon into simplicial cones and take one of the cone, which is simplicial cone. So that's I'm symbolically that I'm writing here. And then take a ray generator kappa 1 and kappa 2. And so that corresponds to these two ray generators. And take a general linear combination with parameter alpha I, so that the kappa is inside of this specified signature from regular form. And then again, this gives us nilpotent action on the H equals. So Lefschetz action it acts on the entire Hosono homology space. Okay, just focus on the even part like this. And then there is there we observe very similar structure here. And then, as I said, as I introduced last time, it's the mirror symmetry is I already said that there are many versions of mirror symmetry. So one very primitive or classical way to define mirror symmetry is something like this. So X is mirror of X check. If there is a family of the X check, mirror Calabi-Yau. Last time I did this star. Yeah, this one I use check. And then family, not only just single family, but suitable compactification where we find the normal crossing boundary point 4. And where we have, just as I explained, nilpotent action, and on the X side, we have nilpotent action, which comes from Lefschetz action, Lefschetz theorem. And then, as I introduced last time, so both to a nilpotent action, one is acting on nilpotent action acting here, this Lefschetz action acting on this even side, and there is a linear isomorphism. That's not only last time I was asked this when I used it like Blackboard. Last time I denoted this Q, but obviously I'm taking general linear combination, so it should be consistent. So it's not just linear transformation of R, but we require that that if we combine this story with the homological mirror symmetry, then there is on this even side there is a table or much downstairs. There are category of PXC and then after the table and where we have the skew symmetric limit of pairing, and then on the other side is higher category, and then the object is Lagrangian submanifold, Lagrangian submanifold, and then the table more class, individual class, and then we have one pairing, which is skew symmetric for simple case. And then this linear isomorphism should be compatible with this integral structure. That's the definition we have. So, two parameters, alpha I and lambda I, are introduced here. And when claiming this equivalence or this relation, so somehow they identify parameters. Simplest way is to just identify that alpha I equal to lambda I. Last time I have shown that I think I have shown that in case of conic hypersurfaces, alpha I equal minus lambda I. So this identification works. So in this part seems to depend on this. But not so essential for some suitable identification we can find. So that's the definition of symmetry. And then now this part I explained in the past. So all this, in case of Calabi-Yau hypersurfaces, there are Calabi-Yau threefold, which is hypersurfaces in total like this. Then everything is very concrete, and then as I have shown, the key ingredient is the secondary polytope. So secondary polytope, one picture is describing the compactification of parameter space, and another picture is the normal form of secondary polytope describing the Taylor form of the mirror. So this how to say, we can go further. This kind of duality, so-called Gale duality, in Fourier geometry So in case this is somehow recaptured what I said last time. Yes. Now I'm going to give you a toric variety. So maybe during my talk I will explain why I focus on this example. So if we go beyond the toric varieties, then in case of toric varieties, of the hypersurfaces or complete intersection in toric varieties, then we can start from the future point of or its generalization, so-called Goldstein form or those kinds of entities. Nice notion in terms of toric geometry. And if we go to outside the toric varieties, there is no canonical way to construct Calabi-Yau manifold. So this is one interesting example. So just for a moment, just forget about the Calabi-Yau manifold and think about the embedding problem of abelian surfaces. So abelian surfaces get and classified by the so-called period matrix. I write here omega. So just like elliptic curve, so elliptic curve itself is just elliptic curve. So modular space is curve, but to get a nice modular space, nice modular space over which we have a universal family, then naturally people come to the level, introduced to the level structure. The same thing happens here. The abelian varieties, if 1, is the standard one, the principally polarized abelian surface, which comes from genus 2 curve. From the viewpoint of constructing modular space, which have a universal family, people naturally come to the level structure. D1 and D2 is level structure. So in this case, this time the polarization. So this polarization condition is integer, not positive integer and non-biased integer, and so this divisibility condition satisfied. So in case 1, case is the principally polarized Jacobian varieties, and then this part is this period matrix. This is the matrix whose imaginary part is positive definite. So symmetry. So this is just defines the torus. Torus with polarization is abelian surface. So consider C2, and then inside C2 consider lattice structure. So I develop lambda like this, and then take a quotient. This is the definition of principally polarized abelian surface. So same thing. So 1 comma tau. 1 comma tau is the the standard construction of elliptic curve with modular parameter tau. Now, basic fact about this abelian surfaces is that with this data, I'm not going to details. So with this period matrix, with data of this period matrix, then we can introduce topologically abelian variety here is just a portion, but lot of structure we can introduce. The first thing is that with this data, the symmetry matrix, so we can introduce, we can define a line bundle, natural line bundle over these quotients. That part, I'm not going to detail, but you know very better than me. Just look at the text. So we have such varieties. And then But I should remind you is that here with this data, so just believe that the natural line bundle comes with this data at the complex line bundle for this portion. And then choose the first chunk class if we calculate based on the definition of this line bundle. Then first chunk class is di, and x and y is real coordinate. So you can read that here. So d1, d1 to d2 is this polarization type. So this says the first chunk class is integral class. And then if you write in terms of complex coordinates, natural complex structure over here, complex coordinate, and then this first class is in terms of we can write down imaginary part of z. That means positive definite. So that means the first class is first class of this complex line bundle is integral and positive line bundle. That means ample line bundle. So because given an ample line bundle, then we can consider embedding problem to certain suitable projective space. And that's the natural questions. We start from this definition of abelian properties. And then if just calculate the sphere of the partial class, and then 2 times d1. This is based on this one that we can calculate easily. And then using Riemann-Roch formula, and this line bundle is ample, so we can apply vanishing theorem. So it's just the Riemann-Roch theorem tells us dimension of a global section. And then after some calculation, dimension of global section is just using this one, d1 and d2. That's just take some British Harris or some time. So that is you can see. If you look at the text, you don't find out. And then, as I said, this line bundle is ample under this condition, and so we can consider embedding program in terms of this global section. So how many global sections? D1 times D2 global section. So embedding space, projective space is D1 times D2 minus 1. That's the embedding space for the area surface. So, I'm sorry, so just I should say before this example I already published this almost over 5 years ago, and I'm still in the end I will show you why I'm coming back to here. One reason obviously this is beyond polarities, and another reason is that the associated to this abelian embedding problem, abelian varieties, growth and progress, so year 2000, around 2000, so for some reason, not so clear, but case by case, we naturally come to the Calabi-Yau threefold, whose fibers are abelian surfaces, just I described here. So abelian fiber Calabi-Yau manifold comes out from this embedding program. And then what I'm going to show is very special case. So D1, D2 equal to the 1,8 case. This case is very nice. Very close to, in some sense, close to the toric varieties, complete intersection in toric varieties that not belong to the complete intersection inside toric variety, just I described in the past talk. So 1,8, just I'm going to focus on from now, afterwards. There are 1,5 and 1,7. The other case is 1,6. We have certainly Calabi-Yau threefold whose fibers are given by abelian surfaces. But I don't know. At this moment, I don't know. I couldn't succeed in finding suitable family where I described where I can find a suitable boundary point to see the inner symmetry in terms of my definition. So anyways, this problem is for me long-standing problem that I want to solve or I want to get into the details. Anyways, so from the reason that I just said, I focus on one form H case. So consider the abelian surface with the line bundle L. So that means more concretely with the data of matrix, period matrix Z or Zij, and then with the polarization type 1.8. And then, as I said, this abelian surface in terms of linear, in terms of global section, we can embed into the projective space. So B1 times B2 is this time 8. So embedding is into the P7. And then, so from here you can easily guess so how the global section for the abelian varieties in this setting. So this is embedding, but all we have is this data. And then everything should be written in terms of this one, period matrix. And then embedding certainly you can already guess. So then these global sections are given by theta function associated with this field. In case of elliptical, this is just 1 comma tau. So sigma tau, we have theta functions, and then if in ellipticals, so if we introduce level structure, then different level structure, not a single theta function, but levels with level structure is dimension becomes too larger. And the same thing here in terms of the Zij, theta function gives us embedding. So that is, yeah, so my focus is, my interest is not that theta function. So some experts are interested in the theta functions and they among them and those functions are interested in mathematics. Theta functions, and guess it gives us the embedding. And the question is okay, so in this way we have embedding to project space. And then natural question asked by Gross and Popes around 2000 is that how the image or the idea or the vanishing idea over the image of this embedding. So I think more concretely, how the equations for the image of this embedding. That's a natural question comes out from this embedding. We have embeddings certainly, but we don't know the equations for that. And then Gross and Popes worked out and the polarization by polarizations. I don't know complete descriptions they gave or not. I don't know precisely, but the 1,D case, 1,D, they were able to find out they are able to describe how the idea of this property looks like. And in this case, 1,8 case is in particular very simple. As I said, the program is idea, find out idea for the image. And then it turns out the four quadratic, the idea generated by four quadratic plus additionally 3 by 3 minus of over 4 matrix. So quadratic. And this part is not so. I'm not going to use this part. But if you write out write down the explicit equation for this cubic. It's not so beautiful. That's a little very complicated. But so they found how to find out the equations here. And for quadratic, just from now on, soon I'll show you the very simple one. And yes, this is their result. So they find out the vanishing idea for the image in this embedding program. Now, so a little bit digression, but let me remind you the theta function. A little bit of details, but it's related to the structure I will use from the theta function. So, on the set of theta function, there is actually the answer is their natural action called Heisenberg group. So how it comes out? Given abelian varieties, and then the their variety is degree 0 line boundary. So take a point of the abelian surface, and then the TP is translation. So as abelian varieties for elliptic curve, the simplest case, the translation addition is there. So that's as an automorphism. And then, so as I said, the line boundary we have, and then by using automorphism translation in the true part of the line boundary, and there's a inverse. Then this gives us the degree 0 line boundary. That means it points to the pure abelian varieties. And then how the kernel? Kernel is this trivial line boundary. So that means so translation acts on L trivially. Z8, the answer is Z8 cross Z8. Kernel of this map is Z8 cross Z8. That's the answer. I'm not showing you this result, that's just showing you the answer. So the point is that the kernel acts on the line boundary of this kernel of its sequence. So that means this kernel acts on line boundary trivially. So in other words, the theta functions are sections of the line boundary. So this kernel acts on the theta functions which we use for the embedding program. So the 8 cross the 8 naturally acts on the sections. That's the picture I want to draw here. And this is I explained here. And actually, when you consider kernel, as I said, kernel act naturally on the theta function or global sections of the line bundle. This explains, this sequence clearly explains that part. And eventually, actually, not this Z8 cross Z8, but rather central extension. Central extension of mu 8 is the essence of the unity secret group. So central extension of this Z8 cross Z8 is the definition, by definition, Heisenberg group. So when act on the sections, eventually the central extension comes out. That's the Heisenberg group. So just you after scaling, so just you may understand the Heisenberg group as Z8 cross Z8. So, and the explicit action is the Heisenberg group is generated by sigma tau Z8 cross G8 corresponds to G8 G8. But this two does not commute, so because of this central extension. And the action sigma is just a shift coordinate 1 like this. Then tau is the multiply the C is the S unit of unity, such as scaling after. So all these shifting properties and these scaling properties, if you like to see it, and then write down the theta functions and how this kernel automotive translation acts on this space update function, this kind of property should answer. In case of torus, it's more or less remain useful. So a little bit detailed part, but I will use this property here soon later, so I explain here. So in case after here, the point is that we think about the embedding program of abelian surface to the substitutable projective space in terms of theta function. Because of theta function, in this setting, there is natural action of the Heisenberg group appears in this embedding program. And Gross Lopez considered the equation for the image. The answer is here. The 1,8 case, let's say the embedding branching idea for the image consists of generated by four quadratic and complicated cubics. In the I think we focus going to focus four quadratic. The fourth quadratic has a form something like this. So very nice form, looks very nice form because of just as I explained this Heisenberg group invariance there. So this is so sigma. Sigma is just a shift index. Index shift is acts as a shift on the indices. So F1 it looks like this, and F2 is sigma. Sigma if we act on F1, and then X0 goes to sigma inverse. X0 goes to X1, and X4 goes to 5, and X1 goes to 6, and so on. So this is these four are Heisenberg group. Order 4 cycling group. And then look at the sigma and how outcome is just the scaling, and so just the scaling the scaling property of these monomials or polynomials same. So in case each fi are not Heisenberg invariant, but in total, as an idea, this defines the idea subset of the idea for the vanishing idea. So in case, so this is explicit form of creation. This follows from the Gross and Lopez. I haven't derived. I'm not playing idea on this one. Just I'm taking this one. And then from the so we came to this whole equation starting from embedding program abelian surface to the project space from x1 to x0 to x7 in a homogeneous coordinate of P7. So coefficients omega 0 to omega 2 is determined by the abelian surface, which we started with. So each abelian surface, we have this kind of equation, these coefficients omega 0 to omega 2. And the main point, it's probably hardest part is that with this, looking at this equation, so we have a given abelian surface, we have three parameters here, and these are I defined here, so just projectively, overall factor doesn't matter. So it gives us a point in P2 if we arrange in this way, and then the point is that the Gross and Lopez, if you look they didn't say in this way, but if you look their paper, and then this map is surjective So this part is not so trivial thing, so you need to work hard to subjective. And after the fiber, this one. I will explain the result. So if assume this is subjective, then the abelian surface just took out abelian variety. Abelian variety is three dimension, right? So modular space is Gij, symmetric complex matrix. So it's complex dimension 3. So given modular this think about this A is a point in the modular space, which is dimension 3. So I'm saying that there is a surjective map to P2 from here. So fiber is dimension 1. So how's the dimension 1? Dimension 1 is tensor of abelian surfaces. And the tensor of abelian surfaces gives us the Calabi-Yau 3-fold. That's their result. And so this is their result. I'm just simply introducing you their result, and my interest is the mirror symmetry of this Calabi-Yau. This is certainly beyond the full equality. So now I described. I said that here that by this map we have the. Two things apart. So this map is from the modular space of abelian surfaces, 3-dimensional to the dimension P2. And then look at from this side. So give a point of P2. I should accept that this is surjective map, and then take a point, and then forget about the embedding problem for a moment. And then we have four modular equation, which defines, that 2 inside P7 is completed intersection of Calabi-Yau manifold, 3-fold. So just forget about the embedding problem, and then you can see this four equation like this. And then the V omega is this locus of photovoltaic inside P7. But this is singular. And then this embedding problem, modular space of abelian surfaces to the P2. And this picture is completely mixed up. Maybe we can recognize how this relative. So simply, roughly saying that this Calabi-Yau manifold, the 3-fold is the tensor of abelian surfaces. Just you can see from this surjective one. That's the picture. And slides are prepared for 60 minutes talk. So let's summarize the properties of the Calabi-Yau 3-fold, which appear as 2 complete intersection in this context, and special form of equation. Last time, in case of toric varieties, what I considered is general form of defined equation. So that compactification is given by secondary polynomial. But this case is special form of the two defined equation. So that's a difference from the first talk. And then for this Calabi-Yau 3-fold, we have following properties. First of all, the defined equation, just as I said, is there is action, Heisenberg group action. Heisenberg group acts on this Calabi-Yau 3-fold, Actually, if you look at carefully, this action is free action, no fixed point on this. And second thing is that the omega is the tensor of the polarized abelian surfaces. Just I said, here from this picture, we have 3-dimensional space, the 2-dimension fiber is 1 dimension. This dimension is sitting here. That's the tensor of abelian surfaces. Then actually it has a base locus that we have to look at carefully. We have defined equation, so we can study this kind of thing. And then base locus is 64, consists of 64 base points. That's the base locus. P1 family of abelian varieties is the omega that is 64 points. It does not move if we change the P1. And the picture is something like this. We have 64 base points, and there they have those. This is the base point gives us the singular. Only the omega is singular Calabi-Yau manifold. Singularity just comes from this 64 base points, which singularity type is ODP. So just 64 ODP this Calabi-Yau manifold has. And then the small resolution we can think about. And if we can make a small resolution, then we will have smooth Calabi-Yau. That's that process, third part. And actually, we can make a small resolution. So this is a schematically I wrote the abelian surface, so that one. And this line is the P1 tensor, P1 for the tensor. And then this point is base point. So according to the P1 direction, so this abelian surface moves something like this. But the base point is fixed. That's the definition of base point. And this kind of local geometry we can see at the 64 point. This is only the singularity of this Calabi-Yau. And what we do is that all 64 points are on the everywhere local geometry, something like this, and there is a abelian surface. 60 points are on the abelian. One abelian surfaces, one abelian surface, and so which is divisor. So around the one abelian surface, just make a drawing up. That's we can do the algebraic geometry or complex geometry. Algebraically, we can do drawing up around the divisor and one abelian surface. And that result is here. If you do the draw up around the divisor abelian surface, then we will have the exceptional curve P1. So small resolution, point is a small resolution we can do globally and projectively. And then after this, we plot this P1 to this form. And then this bottom line, this line is P1 for the tensor, one parameter family of abelian surfaces. And this one is the exceptional curve. So as you see here, so this one P1 is parameter. This P1 is the exceptional curve, but it is a parallel. So this means this abelian surfaces, one parameter family of abelian surfaces are aligned over P1 in the end. So that's the abelian calculation we will have in this setting. So started from the singular to to complete intersection, which is singular, with singularity is 64 ODP. They're growing up like this. We have the smooth Calabi-Yau, and then after plot, we have another smooth Calabi-Yau, which has abelian calculation. That's a very interesting Calabi-Yau. I don't focus. The point is that after blowing up, originally this similar Calabi-Yau has the Heisenberg action, free action by Heisenberg growth. And after blowing up, this action naturally extends to the free action, Heisenberg action. Both the Calabi-Yau threefold, smooth Calabi-Yau threefold, are with free action coming from Heisenberg. That's the result. Just to keep this picture. So this is actually detailed. So and just let me summarize. We started from the family of Calabi-Yau over P2, and then this is 5 by singular Calabi-Yau. After small resolution, we got the family of Calabi-Yau. 5 by this one. And second, after making a plot, and we got the family of Calabi-Yau. 5 by is abelian 5 by Calabi-Yau threefold. That's the interesting part. Now I introduce the Calabi-Yau, and notation is this side of V2, this side I call V1. Both are the same thing, but I mostly focus on V1 part. X from now, and then how the Hochi numbers. Hochi number is before growing up. This is not the precise way to formulate, but before growing up, small resolution, as a senior varieties, picker number is just 1. But I did to get to come to here. I did growing up around the abelian surface. The abelian surface. And after growing up, we got exceptional divisors, additional exceptional divisor. So that explains 2 here. The picker number is 2, and then, as I said, fiber space. So we have abelian surface over P1. So as an Euler number, each fiber has just Euler number 0, and the entire space is Euler number 0. So because of that, and the formation space is 2. And this is not an exact rigorous argument, but the formation space you have to work out more clearly. In case 2 is the right answer. This is a Hochi diagram for Calabi-Yau 3. And you will recognize maybe one is the most easy, simplest case. The 2 here is both scalar moduli 2 and the formation space has dimension 2. This is a very simplest case, and everything we can find out. So both scalar side and the formation side, should be able to see, formulate. You have a lot of abstract formulation, symmetry or many ideas and that. Usually if one side is small, then the other side is very large. So we cannot see both property A and B at one time. So in this case, this is a very special case. Abelian surface, but if you Calabi-Yau has abelian calculation, then always the case like this. 2 is a very special case. Now, this is a Hochi number, and actually historically, this abelian fiber Calabi-Yau studied in this context, in different contexts. And at some time in the history of mirror symmetry or Calabi-Yau the study of Calabi-Yau manifold in the context of mirror symmetry. So some people are interested in the Calabi-Yau manifold, which has non-trivial pi1. So Atsushi studied one case, I think, one class study, and so this Calabi-Yau appeared in that context was studied all days. So as I said, this after drawing small resolution, this Calabi-Yau admits free action Z8 equals Z8, and then take a quotient, free quotient, we will have smooth Calabi-Yau with fundamental group is Z8 equals Z8. So this is Z8, still I think this Z8 equals Z8 is largest order of the fundamental, non-trivial fundamental group. So this Calabi-Yau is still interesting. And then so Gross and Habaneri studied this here. This is not trivial. This Calabi-Yau has not trivial pi1, and they studied this Calabi-Yau. This time for this side they studied the Brauer group. The Brauer group has some torsion part of the H2 or H3, and then they found. This has non-trivial Brauer group. This has non-trivial pi1. How these two are related? So the answer is that this quotient from now I will describe why, because Z8 cross Z8 appeared here already. Z cross Z8 here. So literally, very nicely, take a quotient abelian surface by Z8 equals Z8 gives us real abelian varieties. So this quotient is basically acts on fiber direction. General fiber, this quotient is just that quotient. So fiber-wise Fourier type is this quotient. The only problem is senior fiber. This kind of thing worked out Schneider and this here. So X under this free quotient is interesting. So because Fourier right transform, derivative equivalence. And this quotient is not derivative equivalent. But somehow they studied, and also as I said, this has non-trivial pi1, and this has non-trivial Brauer group, which is under Z8 plus Z8. Fourier right transform exchange pi1 and Brauer group. This is normal. Now the way we study this. So in any case, this side of the result is very interesting appears, and so Z8 plus Z8 we have, and then in that context they just conjecture that how about the Z8 quotient, and should be the mirror to this one. Mirror of this one should be this one, and the mirror of this Calabi-Yau is this Z8 plus Z8 quotient. So that's the naive conjecture. In any case, so we have abelian fiber Calabi-Yau which admits free action. That's the interesting part.
I forgot to ask you, what's the evidence that they are doing that?
Not so easy. Just consider, just create, yeah, no.
It's not a multi exchange.
Yeah, not trivial.
I wonder what's the evidence.
Not statement, just in the end, one single statement, probably this kind of picture we should have. Very weak statements. And because at that time they didn't have a mirror family, and then so what I'm going to show you is the after constructing mirror family, and then this picture is justified, can be justified. Statement is not so rigorous, it's very difficult to wrote in this style. Just in the conclusion section, mirror should be this one. Yeah, maybe we can have more complete with much more complete result. Now, these are all these background about Calabi-Yau 3-4. Then, I thought that 20 minutes is too much. I'm speaking very slowly, so I will speed up. So all this, after here, everything is not my result. So I did lots of best and historical things. And the point is that beyond the toric varieties, or complete intersection of toric varieties, there are many chances you encounter interesting Calabi-Yau. That's probably the universal things. So in any case, from now I want to construct a family of Calabi-Yau manifold of this quotient or X itself. But from some reason I would consider this two quotient. So X itself is actually difficult here. I encountered so far I schematically I wrote family of Calabi-Yau over P2. And then I said that the Heisenberg group acts on the each fiber. Just in this picture, just a point, but the point is supposed to be to complete intersection. In this point, on this complete intersection or small resolution of that, there is natural action of free action of Heisenberg group, I say. And if you look at this total family, and you look at the result with defining idea, I omega, I know, yeah, is a little bit larger group actually acts on this entire family, it turns out. So it's actually algebraically the normal group, and so there's a Heisenberg group acting on the 8 by, represented by 8 by 8 matrices, then the GLHC, and then think about the normal group there. The normal group acts on other symmetry group of the idea. That's the result I use. And what I found is that first I consider the family of this Calabi-Yau and the family of this Calabi-Yau. By this you can visualize this. I mean, precisely after small resolution, family of Calabi-Yau, just not writing so precisely. Then we have this family, and then take fiber direction, take Z8 quotient, so generated by tau, and Z8 plus Z8 quotient in fiber direction, around sigma, and which gives us from this picture, you see the family of P2, two family we have. And then actually symmetry group of idea is a little bit larger group, it turns out. And then if we take out the entire normal group to take the quotient, we can take further quotient here because the idea is invariant. But that is not a good quotient. And turns out a little bit smaller or a little bit larger group than the Heisenberg group. There is a group. I will explain how I came to this group. Some requirements I can do this. The natural requirement later comes out to be. Start from this family. This family is not good to describe mirror symmetry. And find out, take a suitable group and take a quotient of this total space. And then the total space take a quotient about this, and then the downstairs of the parameter space, and then this retriever action on the Z8. And this gives us toric varieties. So P2, toric variety by abelian group, discrete group quotient, again toric variety. Both sides is the same toric variety, but P2 variety this way. And the point is that this is the right family to describe symmetry. This is a picture. So originally P2 has a homogeneous coordinate, omega naught, omega 1, omega 2. But I want to take quotient. I take the overall quotient. So because of that, the H quotient comes out for the parameter space. And then the quotient means they take invariant monomial, and then take approach. That's the definition of P delta. And actually, it write down with all invariant monomials, and then take approach. And then the picture, point of is looks like a P2, similar to P2, but these 3 points are similar. This point has similar A1 singularity, A1, and this A3 singularity. And then just the toric resolution make up, and then right from now I use the local coordinate X and Y taken here. This is a parameter space. I set up the quotient, and the introduce coordinates for the parameter space. And then, as I said, so local system you consider, and for the period integral, associated from 3 form. And this is the standard form for period integral for Calabi-Yau 3 form for complete intersection in terms of residual formula. And then from now it's rather straightforward to find out differential operators which annihilate this period integral. And after some work, it turns out that we have second order partial differential operators and third order partial differential operators. This is enough to determine orders are even integrals. So Gakushuin differential is something like this. Yeah, at this point maybe I'm considering 2 families. One is the X quotient, the other is the X quotient. I mean, the difference is just a discrete quotient. Both sides, if you look at the variation of Cauchy structures of our local system, this difference by discrete quotient doesn't matter. So the point is that this Gakushuin differential operator is the same for these 2 families. Now I'm going to a little bit more details. And then, so as I said, this point of is the point of for the parameter space for the compactification P delta. Compactification is from the beginning P2, already compactified, and then I'm focusing hard to find out the point for P delta. And then we got a Gakushuin differential operators, so look focus on the other discriminant, singular locus of differential operators. Or I mean the File family, and you also look at the generation locus of the family. Then it turns out that there are 2 components for the discriminant. One component is something like this. So over this discriminant, the complete intersection acquires 8 ODPA or I know little numbers. So ODPA appears here, and over this the component of the discriminant, a little bit higher singularity appears. That's a picture, additional picture. And as I said, what we do is that this point of has a singularity, toric singularity. So as I described here, first thing is this graph, toric resolution as a toric varieties, and then I'm just writing proper transform of discriminant locus downstairs here, and still this toric boundary divisors and intersecting discriminant is some tangential, not non-normal crossing appears here, and this point is also singular. What I want to do is everything should be the normal crossing. So what we do is the first thing is this tangential intersection, and after taking suitable number, not suitable time for growing up, and go to the normal crossing situation. And for the second part is this part, and draw one time this part, and then again this part. And and this is a little detailed part. Just believe after this process, everywhere is smooth and divides as a normal crossing. And that's a situation I want to destructure. Now the monogamy. Look at the destructure. And then here I go. Lots of destructure I can observe. We can observe. What's the point? This part is very detailed, so just entire picture I want to tell you. That after growing up, everything is normal crossing boundary divider, and they focus on this B and B tilde, and C and C tilde, and here A and A prime. And other points are not we cannot see the B structure, but here the both A and A prime, B and B prime, and C and C prime. From there, all six boundary points are describe B structure, which gives us a nilpotent action, which I'm interested in terms of viewpoint of real symmetry. That's the result. So I'm not explaining why this happened. I'm showing you the results after suitable definition of the parameter space. After a process like this, there appears this structure, meaning multiple these structures. And then I classified it. So 6 B structure we can read off from that from the model space. A and A prime and A B tilde and B prime, C and C tilde. And that claim is that maybe I should quickly. I identify this boundary point. So as I explained, from the boundary point we can calculate the nilpotent action in lambda, and then based on the in lambda, I look for the mirror side, and then I find that this fits into the A structure of X. A prime boundary point fits to the X prime, which is birational after plot. X and X are related, and B tilde fits to the A structure of this quotient, 3 quotient. And B tilde prime fits the birational to this quotient. And this structure C, to C and C prime, if I compare the S structure, then I can identify these two here. And then my claim identification is look at how to classify these two. So actually look at this integral structure or period integral. So each point we have local natural basis for the symplectic structures. And the point is that analytic continuation, then we can compare these two are same class or whether these two belong to the same integral structure or not. This kind of thing we can work out. And then the classification, this part, and this part, comes from this such a way. So this structure we can read off from the locally, the near boundary point. And then analytic continuation. So I grouped this one and this one. And then claim is that this one is the design integral structure. My interpretation is this integral structure comes from this family of the x portion. And this integral structure comes from the family of this dx plus dx portion. Why? I don't explain it so strongly, so why it's natural, so fit into this one. So, Atsushi asked, the gross and Popescu and conjecture this kind of relation. And look at this structure. Suppose we have family of this Calabi-Yau, family of Calabi-Yau, fiber is this one. And then I claim that for this family, the 4 or 2 boundary points have the same integral structure. So that means should be identified this one. So, from this side, the mirror should be these two. Both x and quotient. Both x and quotient appears from this side. And then for this side, integral structure. So I am considering this family. And then two, or if we forget birational model, then just one boundary point I can see. That's this mirror. So a little bit complication appears, but the point is that all like when constructing Calabi-Yau 3-4, lots of birational model, Aquarium type partners, all kinds of things naturally encountered as a beginning. And then after constructing mirror symmetry and mirror family suitably, you can find out the corresponding boundary point in the measure space. That's global picture. It's the output from the study of this special case. Now maybe 9 minutes too much, so I can still many slides, but very quickly just show you the another aspect. So this is a mirror symmetry part, and my conclusion is just as I said, construct mirror family and look at the parameter space globally, and then if family is nice, then we can find out the boundary point, which we can understand with the A side, so bilateral geometry or fluent type partners. So somehow mirror symmetry is mixed up with what I know geometry to the variation for this program variation for this structure. That's the interesting part of mirror symmetry. That's the maybe conclusion. So afterwards, let me very quickly. Another aspect is mirror symmetry is calculating block fitting variance. So once we find out the boundary point, then we can calculate block fitting variance. And then how about the block fitting variance in this case? Actually, I focus on the abelian calculation over P1. And like this calculation is just single x. And x corresponds to the I identify some boundary point. And then from the boundary point, if we use mirror symmetry, we can calculate the block fitting variance of mirror side. Mirror side is geometry is such like this. Abelian calculation. The easy part is curve counting on the abelian part of the Calabi-Yau. How many curves inside the abelian part of the Calabi-Yau manifold? Generically, abelian surface does not contain the rational curve. And so, very special locus, such curve contributes to the counting program. Actually, it turns out the population has 8 singular points. So, singular fiber is so-called the translation slope, very special degeneration of abelian surface. So, yeah, so maybe just just think. So generically add 1,8 aberrant fiber here, but the 8 special points there, single fiber we have. And then from there, actually counting comes out. So this number are counting of curves. And probably if you don't know, you are not familiar with counting growth invariant, it's rather hard to take it off. Invariants are parameterized by homology class of curve. In this case, figure number 2, so their homology class is generated by 2 classes. One class is section P1, and the other class is line class. Line class is general fiber does not contain line, but single fiber contains line. Class L comes from the single fibers. Sigma and L is the generator for the H2. And then this table says that the curve class is the one section plus additional line. How many lines? So 1, 2, 3, 4, and 8. This specifies the curve class. So N equals 1, beta equals sigma plus ML, and these are counting class. 64, you recognize this is 64 sections, which correspond to the 64 ODP, where I described small resolution. This continues something like this. And 2-section part of something like this. And so, if you look at this make up the generators, these numbers, these are just table of numbers. But if you could define the generating function for these numbers, and then the first line, n equals 1 case, these numbers, if you make up the generating function, then modular forms, eta function, yes. So I'm happy. So now I'm going to talk this connected to the modular forms in the title of this workshop. So modular form, plus a modular form appears somehow, and then this continues. So n equals 2 section, second line, third line, and fourth line, and continue this way. And then, so first line is something like this, second line is something like this, third line is like this and like this. So if you make up generative function, then in this case, modular function appears. In the history of growth invariant, this kind of phenomena sometimes occurs, and then some case-free vibration or elliptic vibration case, this kind of phenomena we encounter. Aberrant vibration case, again I encounter this structure. But I don't know why this kind of structure comes on. That's one of the reasons I'm sticking still. Already I published this result in year 2021 or something, that after 5 years later. Still, I don't have any good idea to explain the appearance of these modular functions. Probably related to the modular space of abelian surfaces. It has dimension 3, some restriction. I don't know. Now this is duality part. This is the Hauser counting. So I believe that it just explain Hauser counting. Beta cancel, beta function appears in display in that number. Actually, generative function was 64 times this number function. The 64 is the choice of section, so just forget of 64. Just choose the section one section, and then the line, the sigma plus beta is sigma plus L, one single line, As I said, the general abelian surface doesn't contain any rational curve. Only contribution comes from the singular fiber. So this is the geometry of singular fiber. So 8 case, the 8 comes, this gives us. Yet that the power is comes from, 8 to the power 8 comes from the number of singular fiber. Something like this. And then 44 is something very combinatorial argument. We can explain 44 and so on. Yeah, counting is something like this, and if we go to higher degree, then have the multiple lines we have to think about, and we have to go to the details about what we can say. So, I talked too much in detail, but just this is a summary. So I introduced the definition of mirror symmetry in very classical terminology, A structure related to Lepschetz theorem, to the B structure coming from the normally mutable functions. So the other isomorphism, mirror symmetry. And then, as I have shown, the one interesting example where we can see the mirror side is the global study of modular space, which naturally comes out from these definitions. And the left-hand side is Keller cone comes out, and the Keller associated Keller cone variation geometry, movable cone, and also the twin chi partner, those kinds of things naturally comes out. Mirror symmetries are related. Just an example. And I don't know how to formulate mathematically, how to prove mathematically. It seems to be very hard. And my point this time is that go to the beyond the toric varieties, still interesting Calabi-Yau there. And if you are lucky, you have to be lucky enough to encounter such a good Calabi-Yau manifold. Once we go beyond the toric geometry, and we don't know anything, so there should be a good chance to encounter interesting Calabi-Yau. That's my opinion. Thank you very much.
Thank you very much for the talk. Are there any questions, comments?
So when you were explaining the structure of this family, so for X model of prime groups, so you used GKZ equation, right? So would you like how are those families related with I guess complete intersections in toric?
GKZ system, relation to the GKZ system is the first talk. This time is this maybe show you. This special family is not directly related to GKZ system.
So this equation this differential equation that you work with the period integrals are not.
Not, I mean the specialization of GKZ. So large parameter family of GKZ, and then specialized and lower dimensional loci. In this case, you can write down GKZ.
So this is specialization of GKZ.
GKZ system. But the differential operator does not come, in that sense, does not come from GKZ operators. That's the reason why in this case I was able to solve. Very close to ZKZ, but not the ZKZ. That's the reason that this is so beautiful. So I want to go as I said, this is 1,8 case, 1,6 and 1,5 and 1,10. If you look at the extent of this story to other cases, probably distance from ZKZ is far. far more compared to this one. So because of that, I couldn't come to a nice situation. At least now, I'm trying very hard.
Any other questions?
Can you go to the number of table with n and n indexes? Oh yeah. So it seems like when we fix n and enlarge, it vanishes. Is it okay?
Oh, this bunch,
Yeah, why is that?
There is a section. Number section is that there is a reason. There's a simple reason. That doesn't come to my mind right now. Something related, not exactly related to this one, but sometimes.
Maybe related to transition.
Transition?
Yeah, if you have a conical transition, then you know that in the sum formula you only get a finite number of terms. In sum together will go down to the formulation of the downstairs model. That will force still finite. So the two parameter is bound. So the Ishmael, the summation Ishmael should be bounded by the other direction, the number. So it looks very much like
I see.
in this.
Some reflection. Symmetry.
Yeah. So it's especially for conical transition type 1.
There is a cone described by extreme ray.
Yeah.
This is a cone.
Yeah. And if you see some table like this, bounded, no zero, then you will see type 2. That's exactly the next talk will explain.
So this table is left cone. This side is around here. This one is extreme ray. Dual of this one.
So we actually can see some geometry directly from the table.
Any other questions, comments? I have a question. So you studied the complex moduli of the x over zh or x over zh cross z. What about x itself? Was it studied by Calabi-Yau?
Yeah, that's from technical reason. I couldn't come to the nice family. So around here, I'm not telling you this theory, just my calculation. This worked out. So that's just I'm reporting. And just the interpretation is so nice. So I think it makes sense. So I experiment. That's what I'm saying. That once you go to beyond theory, we have to many experiments.
Actually, I have one question. So I remember when you wrote this paper, you are addressing the problem on BCOV, right? So you actually says that something like this is a two-parameter model, and you are saying this is a good model so that the boundary contribution actually doesn't matter. You can still solve the BCOV by just like
It's expected. So this is just genus 0, but I calculated up to genus 2, and still this more modular form appears.
Also up to genus 1.
Up to genus 2.
Up to genus 2. It's okay.
And then my hope is that this PSI modular form is with genus parameter in the end, nice automorphic form, those kind of thing.
I mean, can you comment what you have in mind? Why the other boundary should not have trouble to fix the holomorphic anomaly equation? Because in general, of course, compatible, but why in this particular?
I think I don't remember exactly what I said. Same thing. The difficulty is not so big difference. This case too, the fixing harmonic term, that ambiguity program is still here.
Still here?
Yeah. And somehow the modular property, something like this, if we have such a thing, then we can replace the fixing program to the modular properties. Just kind of conjecture that imposing, requiring the modular properties. We can do this on proof.
Okay, thank you.
Any other questions? Comments? If not, let's thank the speaker again. Maybe it's, 50?